Okay, now we'll switch gears and quickly go over some of the laws of thermodynamics. Again, like I said, if you want a deeper understanding, you need to take a physics course. Okay, so there are 4 laws of thermodynamics. The 0th law says two systems are in thermodynamic equilibrium, meaning they do not exchange net heat. So if you have two objects, they're in thermal contact and they do not exchange any heat, that means they're at the same temperature. So what this law is saying is if two objects do not each two systems are both in thermodynamic equilibrium with the third system, then they'll be in equilibrium with each other. So they're all at the same temperature, essentially, is what we're saying. The first law of thermodynamics states total energy is conserved. And once scientists realized that heat was a form of energy, uh, the first law of thermodynamics essentially includes heat in the conservation of energy principle. The second law says, so for instance, we'll do a little diagram. So hot, cold. So let's say part of the room is hot and cold. Um, um, what you see is in nature, okay, cold, hot. Heat always flows from the hotter to colder region. You never see this happening. Okay. Now, this would never happen. So, in in this diagram, all that happened was energy moved from here to here. The total energy of the room was the same. Well, why doesn't this happen? That energy moves from here to there, and the total energy of the room would still be the same. Okay. So energy is redistributed. You only see this in nature, and that's because when this happens, when energy is redistributed this way, what is happening is the entropy of the system is increasing. Okay, and that's what the second law says. The second law says only processes where entropy increases occur. In this process, entropy would decrease, and so this process never happens, and that's what the second law says. The third law says it's impossible to attain absolute zero temperature. Okay. So the temperature of an object, so for instance, if you have a gas molecule, if you have a gas, so think of the gas in your room, the hotter the gas, the faster these molecules are moving. Okay, so now as you cool the gas, these guys are getting slower and slower, and the best you can do is stop all the molecules. And when you stop all the molecules, you have reached 0 degree Kelvin, and you can't cool that gas anymore, and that's absolute zero. Okay. So the 0th law of thermodynamics, the law implies the thermodynamic state of a system can be defined by a single parameter, the temperature. Okay. So the temperature of a system specifies the state of the system. Okay. By the way, here's the ideal gas law. For an ideal gas, the pressure, volume, and temperature are related like that. N is the number of gas molecule, and K is the Boltzmann's constant. Okay, so here's how we define absolute zero, 0 degree Kelvin. So what this graph is showing you is the pressure of a gas versus temperature. So what this is showing you is as you cool the gas, so this is cooling the gas from 100 degrees to 0 degrees Celsius, not Kelvin, Celsius, the pressure is dropping. And so it's logical, as you keep dropping the temperature, the pressure will keep dropping. And the pressure will go to zero when all the gas molecules have come to rest. And this is minus 273 degrees Celsius. So minus 273 degrees Celsius, and we call that 0 degree Kelvin. Okay, so that's how the Kelvin scale is defined. Okay, so the first law of thermodynamics is just a conservation of energy principle with taking into account heat. Okay, so let's say you take a gas and heat the gas. What if this piston is movable? You can put a weight on the piston, and that weight can be lifted. So the expanding gas will do work. And here's what the first law of thermodynamics says. Again, like I said, it's a conservation of energy principle. The heat added to the gas is part of the heat goes into increasing the internal energy of the gas, making the gas molecules go faster, and part of it is used to lift the weight to do work. Okay, so the energy principle says any heat you add goes into either increasing the energy of the gas or doing work, and that's the first law of thermodynamics. So the second law of thermodynamics says, you all know this fact intuitively, heat will naturally flow from a hot place to a cold place. Heat only flows from a hotter place to a colder place because entropy increases in that direction. Okay, uh, so and we make use of this natural flow of heat. It's the transfer of heat from a hot to cold that allows thermal energy to do useful work. As it travels, um, we use some of that heat to do work for us. Okay, that's what heat engines do. Okay, so speaking of heat engines, so here's a cartoon model of a heat engine. A heat engine gets heat from a hot reservoir. It absorbs heat from a hot reservoir, converts part of it to work, and then dumps out the rest of the heat. So, for instance, your car is a heat engine. It gets heat by burning gasoline in your engine. You use some of that heat to convert that to the motion of the car, and the rest of it is thrown out as exhaust in the exhaust. Now, here's the outrageous thing about your car. Your car is about 20% efficient. What that means is for every 100 joules of heat released by burning gasoline, about 20 joules of it is converted to the motion of the car, and 80 joules is thrown out uh, in the atmosphere. So for every $5, $1 is converted to motion, and $4 is thrown out the window. Okay, so that's what a heat engine is. It converts some of the heat to work. So you ask, is it possible to convert all of the heat to work and not waste anything?